Okay, well, this is essentially Tuesday of this week's lecture, and I'm going to have two parts of it. So this would be Tuesday's lecture, part one. We're going to do a bit of chapter 4 and then start it on chapter 5. Section 4.2 is about fluid acceleration. Pretty interesting topic. So ideally, if you were to go work for Intel on heat removal versus airflow, if you were going to go work for Lockheed, doing airplane design, etc., where someone needed you to model fluids, here's kind of maybe roughly what you would do. You would start by observing some flow. So this could be like a airfoil, a section of a wing, and we see the fluid moving over the wing air, and then be able to come up with some analysis where you would get things like velocity. And from velocity, we could use the Bernoulli or other equations to get pressure, to get density, and finally, we might even be thinking about acceleration. That's important. Okay, over here, no need to copy this down. I talked about this last time. We're going to start a little bit more basic and get you going on analyzing velocities and acceleration. So we're going to start by giving you a velocity vector. Okay, give you a velocity vector, and hopefully, if you've gotten going on homework number 4, or you do soon, you will see a good example of that type of problem. And we want you to actually use this function here to determine some velocities. Also, we want you to be able to determine the streamline equations, and that is a very basic equation from last lecture. Then we would like you to be able to do a neat plot. What we're adding to it with this portion of the lecture is we would like you to go from this expression right here, the velocity expression, and be able to come up with the acceleration expression. And there's some good thought there. Finally, we'd like you to add some accelerations to the plot. So maybe to give you a little feel about what's going on, I'm going to go to share screen and let you take a look at an example of something that's all done and talk about it really briefly. So this is an example where we have some fluid and it is essentially encountering on the bottom some sort of surface, and over here it might be some sort of wall. So the fluid's coming in from the left, and you can see that from the velocity vectors. The velocity vectors are those arrows that are solid, and you can see that they're coming in from the left. They're all coming in from the left. And because of the presence of the wall, it ends up turning up, okay? Hey, this is something actually that you would be able to do mostly based on last lecture. You could plot some velocity vectors, and they've got quite a few velocity vectors plotted there. They've added streamlines. The brown are the streamlines, and everywhere the velocity vectors are parallel to the streamline. And then what's new is we've added some acceleration vectors. Okay, so when we're all done at the end of lecture today and you've finished off homework number 4, you should have some idea about how to create a plot like that helps us visualize fluid flow and get some numbers up there that allow us to quantify fluid flow. So part of this is visualization. I mean, how do we actually visualize acceleration for a fluid? And here I'd like to again do a quick video. I realized last time that the videos, the Khan Academy video I showed, the sound didn't show up. I provided a link so that you can actually view that video again. I think it's pretty useful with this velocity vector stuff. Doing another video, and we're not going to worry about the sound. We're going to try to look and see whether there's acceleration or not. So I'm going to go to share screen and see if I can get to that other video. Give me just a second. So with this video, the concern is not the sound. The main thing I want you to do is say, hey, does it look like that fluid's accelerating? So we'll talk about that. We'll work on that in just a second. So here we've got some fluid going over a wing. Sorry about the audio stuff. I'm kind of working on that a little bit. So there's this fluid going over the wing. What they have is they actually have some smoke that's being generated, and that smoke is flowing from one side over here and going across this wing. Kind of a nice image. And they're going to do a couple things to try to help us see whether there is acceleration or not. They're sending pulses of smoke, and then the video is actually being recorded. And so we're going to see is there any fluid acceleration? what we're supposed to say is, yeah, okay. If you look right now, you can see that the smoke above the wing has moved further than the smoke below the wing. And so there is a difference in speed at the top versus the bottom. The way I would put it, and this is a little bit beyond my experience, I'm not aeronautical, but the way I would put it is it looks to me like the bottom fluid is slowed down. Over here, initially, all the fluid was moving at the same speed, okay? And now this stuff is behind the stuff above. Okay, I'm sorry, it looks like my play has gotten a little bit slow. But once again, you can see even greater difference between the fluid above and below. So we definitely have some acceleration going on in this case. A general idea that the person who made this video is trying to make is, hey, the fluid is faster above than on the bottom. And as a consequence, thinking about the Bernoulli equation, we're going to have less pressure above than below. Okay, good enough on that. Hopefully give us a chance actually to visualize acceleration. All right, so before we go on doing some computation, I'd like to make the point that fluid acceleration is pretty different than object acceleration. If we had some sort of object like a car and we're trying to get an acceleration, it might be helpful actually to visualize it at two different points. So the car might be going 20 miles per hour here. It's going to move over there, and it's going to be going faster when it gets over to the second point, say 30 miles per hour. And we can get the rate of change of velocity by thinking of the fact it's going 20 miles per hour here, changing to 30 miles per hour there, and coming up with the acceleration from those two bits of data. All right, that's not super precise, but it's definitely the case with fluids. We actually focus on a point in space and think about what the acceleration is at that point in space. I'd like to do a couple examples to illustrate what's going on. So this one you might want to at least just copy down this vector to remind yourself when you, as you're say studying for test one, hey, we actually talked about a vector where there's a time element in there. So vector, that's 2t times I hat, that's a velocity vector. And I've got 4 points right here. So this is 1, this is 2, this is 1, this is 2. I've got these 4 dots right here. And I'm going to try to I'm going to ask you guys to try to visualize the velocity vectors at a certain time. And then eventually we'll just focus on the point 1, 1. Okay, so let's just start with t equals 0. What are the velocity vectors at these 4 points going to look like at t equals 0? I'm going to pause and let you think about it for a second. Okay, pretty simple. We put 0 in here, and we get that the velocity is 0 at all those different points. This expression right here doesn't vary with x or y, and there's no z involved. And so now we would have velocity equals 0 everywhere. Okay, what about t equals 1? What about time is t equals 1? What do the velocity vectors look like? Okay, so I take this t equals 1 and I put it in that expression there, and I get that at t equals 1, the velocity vector is equal to 2I hat. Okay, well, that means that the velocity is 2 in the x direction at all these points. And so if I focus at this point right here at 1, 1, is there acceleration? Well, there's acceleration if the velocity changes. Earlier, the previous one we did at time 0, we had no movement. Now we have movement. This might be an example where maybe there's some sort of hose or something like that, some sort of tubing, and there's a valve in this tubing, okay? And this valve was already all the way shut, okay? And then at time 0, the valve slowly started opening, so we started getting some flow here over there, okay? So now if I change it to t equals 2, okay, what's the velocity field going to look like? Well, now I'm going to put 2 in here, and I'm going to now get instead that the velocity is equal to 4 times I hat. So all these velocity vectors are going to be twice as long. Has the velocity changed at 1, 1? Absolutely. So we're at this particular point, 1, 1 in space, we're getting acceleration. In fact, we're getting acceleration at all the different points. And we can say that at any particular point in space, the movement of the fluid is changing, therefore there's acceleration. Okay, second example. So I've depicted two flow fields. These black lines are supposed to be streamlines, and I've got a couple different velocity vectors, and we are just going to focus on point A. Here's the picture at time 0. A little bit later, time 1, the picture looks like this. Okay. Even though my drawing's not exactly right, I intended this picture to look like exactly that picture there, and I want you to think about, is there acceleration at A? So I might encourage you to pause and think a little bit. Is there acceleration today? So initially, I might say there's no acceleration at A, because if I take a look at this velocity vector here, it's 4 meters per second. And then later on, it's also 4 meters per second, and I intended it to be in exactly the same direction. So it looks like there's no change in the velocity of A, okay? But if you think about what's happening to the fluid, any fluid that passes through A, it's changing direction. It was going this way, and a little bit later on, it's going to be going up at an angle. And for something to change direction, there needs to be acceleration and force. So even though the velocity, in this case, even though the velocity vector at the point remains identical, we still have acceleration. And these two possible ways we can have acceleration. One, because the velocity at a point in space changes with time, or because that there are other effects associated with the fact that we have a fluid moving and continual fluid coming along that can change in ways as it leaves our certain point. We have another way that we can get acceleration. So the acceleration vector is pretty challenging. I'm going to get it up there and we'll work with it a bit. Okay, so here's our marching orders. What we're going to try to do is learn how to understand and use equation 8.3. I wouldn't write this down. What I was trying to say, what I was explaining previously was the acceleration for a fluid, that there's a time effect at some point in space, that point right there. The fluid can be going faster at a later time than at a certain time. And there can also be spatial effects. Any fluid at this point right here at a later time is going to be somewhere else. And its fluid as it moves to the somewhere else, its velocity as it moves to the somewhere else can be different. That requires acceleration. So here's the equation to write down. It's equation 4.3. This is the time effect. So at our particular point in space, the velocity can change with time. And this right here, I'm not going to explain, but that comes from vector calculus, and we can basically take our u value times dv dx, v times dv dy, and our w expression times dv dz. And in ME120, you're not going to end up worrying about that. So take a second to write that down, and we're going to get going with an example. Sorry about that. Hopefully, I'm sorry, I made some mistake on my pausing. Hopefully this is all working out. But in any case, continuing with this, we can see that for this particular point right here, 1, 0, this equation is simplifies to y equals 2 ln x. And if we plot 3 points, that's probably pretty good enough. So we got through 1, 0. I'll guide you through points that you might select sometimes, but E is a good short point to choose because ln of E is 1. So that would go through 1, 2. Okay, and finally, if you had some very small number like 0.1 or something like that, the natural log of a number less than 1 is negative. So you're only going to get the negative number. So we get that familiar logarithmic type curve that goes like that. Okay. Good. Hey, what are the acceleration vectors going to look like? And that is what we're going to work on next. So ME120, The W term, the term for the velocity in the z direction, is oftentimes 0, and that's true in this case. And so if we take a look, we have 1, 2, 3, 4, 5 terms to fill in. So let's go through them really quickly. I'll get a list up on the board, and I encourage you to pause and see if you can figure them out yourself. But here's the quick list. Okay, we need to figure out, okay, dv dt. We need to figure out u. We need to figure out dv dx. We need to figure out v. And we need to figure out dv dy. Easy enough, but just make sure you know how to do that. Well, giving the reasoning again, if I take a look at this function right here, there is no t. This is a steady state example where the flow is not changing with time. Maybe we've got some fluid flow that's going around a gentle turn like this, where it's going up and it's turning like that. And that's happening continuously, so dv dt equals 0. Okay, what's u for this function? Equals x. That's the u term right there. Okay, what is the derivative of this stuff with respect to x? Well, what you do when you do a partial derivative is you treat everything else like constants. So I'm going to treat this like a constant, this like a constant, this like a constant. So let's go term by term. Here I have a constant times x. The derivative of x is 1. The derivative, and so I end up just getting I hat here. How about the derivative of the second term? When I'm doing the partial with respect to x, I consider these constants. So that is actually going to be 0. So I get I hat plus 0, which is I hat. Okay, if you don't remember that from vector calculus, that's okay. I'd pause and do the next part yourself quickly before I do it, but I'll get going, keep going myself. What is v in this expression? It is the vertical component, and that is 2. Okay. And what is the partial of this respect to y? Okay, well, I don't see any y's in there, so this is not changing at all with respect to y. So there are my terms, basically. I've got all 4 terms, a 0, an x, an I hat, a 2, and a 0. So now I just fill all those terms in there. This is 0, okay? U is x, ev dx is I hat, so I've got x times I hat, okay? And v is 2, dv dy is 0, so I'd have plus 0, and we are done. The acceleration vector for this flow is given by x times I. Okay, let's see if that even makes sense. We're going to go to 2 different points and plot the acceleration. So if I take a look at this point right here at 1, what is the acceleration at this point? Well, I fill in x equals 1 there, and this is a unit vector in the x direction, so I get an acceleration of 1. Okay, does that make sense? This fluid is flowing up, and as it moves, it starts bending to flow more horizontally. So that makes sense that there would be an acceleration that way. There's an increase in fluid speed in the x direction. Okay. Hey, let's do one other point. Let's do this point right here. Okay. This point has the coordinates x equals e, y equals 2. So I'm going to fill the e in here like there, and I get e I hat for the acceleration. And so here, e is about 2.7. So here I get an acceleration of 2.7 in that direction, a much larger acceleration. And that should make sense because it looks like the fluid is moving more and more horizontally. Horizontal speed is building up. There is velocity, there is acceleration in the x direction. So there's an example typical of what we're going to ask you to do in this class. One more example, and then homework number 4, and also a bit on number 5 will give you practice with this. So we could say we got some fluid moving in the x, moving two-dimensionally. Maybe maybe it's water, and we're looking down at the water. So we have some sort of water over here like this, and we're looking down on it. How's that water moving? Okay. Well, ideally, we would be able to say to you, look, I'd like you to depict the flow in the XY plane, but we're going to guide you a little bit more through it. So let me give you some guidance on what we're going to do. Same list as I had earlier. Well, the first thing you'd want to do is figure out some velocity vectors so you can start plotting. And in this case, I'm going to prescribe some ones that you do. I'm going to have us fill out this chart. It might be first to write down what's the expression for the horizontal velocity and what's the expression for the vertical component of velocity, and then just start filling in this chart. Thinking about it for just a second, the horizontal velocity is equal to y. That's the thing in front of the I hat. The vertical velocity is negative x. It's the opposite of what the x coordinate is. So we could go to any point in the plane, like this point right here, and we could figure out the velocity by taking the horizontal velocity as the y component, and the vertical component velocity is the opposite of the x component. A little bit of work and it'll reveal what's going on. All right, so let me do the first one with you, and then I encourage you to finish this off. All right. So at point 0,2, point 0,2, okay. 0,2, what is u equal to? U is equal to 0. Pardon me, u is equal to the y coordinate of 0,2, and what's the y coordinate of that? It's equal to 2. Okay. The horizontal velocity is equal to the x component, and the x component is 0, so that's 0. Okay. What would be the magnitude of the velocity? In the previous lecture, I forgot to put these absolute value signs. That's how we symbolize the magnitude of the velocity. So that would be the square root of 2 squared, pardon me, plus 0 squared, and that's going to be 2. Okay. So what's going on at this point? We have a velocity vector with magnitude 2, okay? And it is in, it's all in the x direction, there's nothing in the y direction. So at that point, we would have a velocity vector like that. Okay, let's go ahead and let you finish it off. I would like you to fill in this grid, and then I'm going to actually plot the velocity vectors. Got a couple lines filled in. I'll do the last 2 lines with you. So if I were to go negative 2 equals 0, that's this point right here. Okay. The horizontal component of the velocity is the y coordinate. That y coordinate is 0, so that's going to be 0. The vertical component of the velocity is the opposite of x. Well, x is negative 2 here, and so the vertical component of the velocity is going to be 2. Hey, what's the magnitude? I square both of these, add them, and take the square root. That's going to be 2 as well. Might as well get that up there. I tried to make this a length 2, this a length 2, and this one right here would be a length of 2, and it has no motion in the x direction and only motion in the y direction. Okay, so I've plotted 4 velocity vectors, trying to get a feel for what this fluid's doing. Let me do one more, okay? 0, 3, that would be a point out there like that, okay? The horizontal component is equal to the y coordinate. The y coordinate is 0, so that is equal to 0. Okay. The vertical component is the opposite of the x coordinate. The x coordinate is 3, so this would be negative 3. Okay. And then if I just do this velocity magnitude calculation, I get a velocity of a magnitude of 3. And so the velocity vector right there is actually going down like that, and it's 1.5 times. All right, some things we want you to be able to do. Plot some V's, I've done that, okay? We'd also like you to be able to come up with a streamline equation. So, hey, I'd like you to challenge yourself. See if you can look back at last lecture. What is the equation that allows us to figure out the streamline equation? Okay, hopefully got that. This is something that should be on your equation sheet for test 2, and also that you practice some. Hey, for a velocity vector field that's 2-dimensional, the streamline equation can be given by dy dx is equal to v over u, and we need to take our information and try to solve that. I'll get going on it myself, see if you can make as much progress as you can on your own. All right, there's my next step. I know that v was equal to negative x, and u was equal to y, so I filled that in, and now we need to go back and do our calculus. We're going to try to keep these functions really, really simple, but on the other hand, you are going to be held responsible for doing the integration. So every example we do in class, work till you understand how to do the calculus. Every example in homework, same thing. So in this, we really have two main options. If we have something like dy dx is equal to something like cosine x, and that might be as complicated as this gets in this class, we can go backwards and say, okay, what is the function for which the derivative is cosine x? That's option 1, go backwards. Second option is what's called separate the variables. And this case like that, on this case over here, on the right side, we only have x's. We can go backwards. In this case, we have x's and y's, and in that case, we need to separate the variables. So I'm going to hold you responsible for being able to do simple integrations in that case. See if you can get the separate the variables and keep going. Get all the y's on one side and all the x's on another. Okay. So I moved all the y's to the one side. I took this y and moved it over here. And I took this dx and moved it over there. And now I have y dy, only y's on the left side, only the x's on the right side. And it is a legal mathematical move to integrate both sides. So what we want to do is integrate both sides and see how that turns out. Well, the integral of y dy is 1/2 y squared. The integral of x dx is negative 1/2 x squared. And when we're doing antiderivatives like this, we could also have a constant. So there could be a constant here and a constant there, but we can combine it into a single constant, and that's plus c. So hey, for me, at this point, that would be 100% full credit. It turns out there could be a much simpler way it could be described, and that would be that we could take this x squared and move it over to the left side, and we get 1/2 y squared plus 1/2 x squared equals c. Don't like that 1/2, so I can multiply everything through by 1/2, and this just represents some arbitrary constant. So if I multiply by 1/2, I still have an arbitrary constant. So this is a good answer right here, but x squared plus y squared is equal to c is a better answer. So what have we done so far? We've plotted some velocity vectors that help us understand what's happening with this fluid. We come up with the streamline equations, an expression for all the streamlines. And as noted last time, then what we try to do is plot a curve or two. And in this case, we're going to plot the curve through x equals 2, y equals 0. Okay, so see if you can get that yourself. Well, first of all, it's worth getting the equation. So if I put 2 in here and 0 in here, I get 4 equals c. So that tells me that x squared plus y squared is equal to 4. That's the equation we're trying to plot. For the most part, we have pretty simple functions. So hopefully you can go back into memory. What is of basic, algebra 2? What does x squared plus y squared equal 4 look like? That is a circle of radius 2. So over here, I could add a circle of radius 2, and bear with me, my circles aren't going to be all that beautiful. But I'm just trying to get something rough up there to figure out what's going on. Looking to me like I'm going to have a little bit of egg shape to it, but not bad. Okay. And now we've got a streamline added to our plot. And it makes sense. Do you see that the velocity vectors are tangent everywhere to the streamline? What's going on with this fluid? Well, this fluid is swirling. It's swirling around in a circle. And over here, there might be another streamline where it's actually swirling around in a bigger circle. So this is, this sort of equation would be how we would represent swirling flow. All right, and then the last thing that we want to do, if you think back at that list we talked about, is we would like to figure out the acceleration vector and maybe add a couple accelerations to that plot. And I'll go ahead and erase the board and get going on that. Okay, so you're pulling out your equation that allows us to get acceleration of fluids. I skipped the W term because this is two-dimensional flow, and that's the most part we're going to stick with. I also could have saved myself some ink by skipping this term right here. The rate at which the velocity vector is changing with time, because if I look at this blue vector up here, there's no letter T in it, there's no time. And let's take ourselves through it then and see if we can work this out. I'm going to kind of space it out and make it a little bigger. I need to figure out what U is for this vector. I need to figure out what dv dx is. I need to figure out what v is for this vector and figure out what dv dy is. So let's go slow and make sure we got it right. Okay. So u is the term in front of I hat, so that's equal to y. That's the horizontal component of the velocity. It's equal to the y. Okay. dv dx. What if I took the derivative of this with respect to x? The first stuff, maybe I'll write it a little bit larger down below. Y I hat minus x j hat. This first stuff here, its derivative with respect to x is 0. This derivative with respect to x, the derivative of x is 1, so that'll be j hat. But I got a negative there, so I got to be really careful. So I get negative y j hat. Okay. All right. Let's see if you can get the other part yourself. So I need to figure out v. I need to go to this function and figure out v. So v is the term in front of the j hat, and so that's negative x. Okay. And then I need to take a look at this velocity expression and do its partial with respect to I, and I am getting the partial of this with respect to y is 0, whereas the partial of this with respect to y is I hat. So there we go. And I'm going to pause for a second and make sure I got that right. So let's finish this off by filling in a chart where we get 3 acceleration vectors at these points here. Give it a shot on your own. And if you haven't paused the video, well, I'm going to keep going. If I were to go to 0, 2, that's this point right here, what does the acceleration tell me to do? Okay, take the negative of the y coordinate. The y coordinate is 0, so I don't need to do that. And then I need to take the negative of the x coordinate. The x coordinate is 2, so this would be negative 2 I hat. Okay, so that tells me that the acceleration is in the negative x direction. So if I were to put an acceleration vector up there, it would look like that. Now, I probably should have worked out all these before so I could decide on my length of my arrows, but that's the acceleration at that point. Hang on for just 1 second, please. So doing 0, 2, okay, that means that's this point up here, x equals 0, y equals 2. I fill in 0 here for x, and I fill in 2 for y, and I get negative 2j hat. So that means the acceleration at this point right here is down at negative 2. So there's that acceleration at that point. Okay, let's do 2, 0. That means I fill 2 in for x. Negative 2 I hat. That's the acceleration, negative 2 I hat. Okay, so the acceleration there is in the horizontal direction, and magnitude 2. And if I do one more point, 0, negative 2, I fill negative 2 into the y coordinate. Negative of negative 2 is positive 2. I get 2j hat. So I get an acceleration that is up. And hopefully this looks familiar to you from circular motion. When we have stuff going around in a circle, the acceleration is towards the center of the circle. So we would get the same thing. Okay. All right, so once again, I would love to have do problems where you visualize some sort of flow field, think about the math you know, come up with a velocity vector equation yourself, come up with a streamline and start working towards working out pressures. But for right now, we're going to give you the velocity vector, ask you to figure out and plot some velocity vectors, figure out the streamline equations, figure out a particular streamline and add it to your plot, and also figure out the accelerations. And that does it for section 4.2. All right, a bit more to finish off the first half of essentially the June 9th, the Tuesday lecture. 4.3, control volumes, no equations, just the concept of a control volume that's used in engineering. So, hey, for fluid flow, it turns out that there might be 2 overall analysis approaches if we have some sort of flow field going on. One might be, if we're trying to figure out, say, what's going on, just for example, with forces, we might follow an individual particle and try to figure out what's going on as it moves from this point over here to this point over here, and try to think our way through that and do that for several different particles. The other possibility we could do is we could just focus on what could be called a region in space, and then do what could be called an in-out analysis. Okay, so I could just pick some sort of arbitrary region in space. I shouldn't have said arbitrary. I pick a region in space wisely, okay? And then I do some sort of analysis about what's going into the space and what's going out of the space and try to figure out what's going on. So, for example, if the fluid goes into the space with a certain speed and goes out with a different speed, while it's in this space, something must have happened to the fluid, and we might be able to use some equations to figure out the process based on the difference in out versus in. Well, that control volume approach is used all the time in fluids because oftentimes we're interested in the interaction between a fluid and some sort of object. So a really good example where we might do a control volume approach might be something like this fan here, like this. Okay, this fan, I'm sorry, I've got it tipped just a little bit. Well, there's fluid moving in on one side and fluid moving out on the other side. And we might be interested in the force that the fan puts on that fluid. And that might be able to help us size the fan if we wanted to create a certain outflow, size the motor, size the wiring that goes into. Hey, a lot of engineering is about sizing. Well, if we're trying to size pumps, fans, pipes, turbines, compressors, heat exchangers, and all sorts of things, the control volume approach is very useful because we're going to have fluids flowing in, flowing out. We define our region in space basically as the perimeter of the device, and then we do an in-out analysis, and that is described in section 4.3, but chapter 5 is all about doing that in and out analysis. Chapter 5 is a pretty deep chapter where we take all sorts of devices from simple as a pipe to as complicated as some sort of advanced type of pump, and we do an in-out analysis. And if you look at chapter 5, they do it for mass, they do it for momentum, they do it for angular momentum, they do it for energy, they do it for entropy, and they do it for enthalpy. We can compare enthalpy in, enthalpy out, and get some sort of useful calculation as a result. Hey, today we're just going to start with mass, and that'll be good enough for today. Okay, mass in and mass out. It's not going to be 2 kilograms in and 2 kilograms out, but it's going to be flow. So we're going to compare basically m dot in versus m dot out. That's what we're going to do in this case. Okay, do they have to be equal? Well, please don't write this down, but let me give you an idea really quickly. What if you saw that? Again, you're not writing that down. That would mean there's more into this pipe than out of this pipe. So m dot in is greater than m dot out in that case. Well, a good question to ask is how long could that go on? Okay, could that go on for a minute? I think not. In a minute, that would mean that there would be 4 times 60, 240 kilograms, say, of water that came in. And over here, 3 times 60, 180 kilograms that went out. Okay, that means every minute, 60 kilograms would actually be being added to that pipe. Hey, 60 kilograms per water, eventually that pipe's going to burst. So we can't have in not equal to out for any control volume for very long. In general, what we're going to do is what's called the steady state case, okay, where there is no change in the content of our control volume. And so we're going to have m dot in is equal to m dot out. Okay, so for control volume at steady state, we can, if we're doing a mass comparison, we can write a bunch of different equations. So one equation would be that m dot in is equal to m dot out, okay? Or we could use subscripts 1 and 2, all right? We could say mass flow rate is equal to, I'm going to go to 1 and 2 now, density times volume flow rate. So this would be true as well. Sorry about that. That should have been 1. There's another useful equation. And if you recall, volume flow rate is velocity, average velocity times cross-sectional area. So another useful equation would be Q1 V1A1 is equal to, probably rho 1 V1A1 is equal to rho 2 V2A2. And hey, but this is not all that new. We actually derived this equation when we were working with the Bernoulli, but we're just going to practice it a little bit more for control volumes. Another quick idea before we do an example. Okay, if we have some sort of flow, and again, I won't write this down, trying to give the idea. And we're going to use what's called the control volume approach. That means we define a region in space, and a lot of times if you look in your book, it'll be a box or some sort of rectangle. This might represent the fan that I held up earlier. Almost every textbook out there, sorry about the glare on the board by the way, tends to use dashed lines to represent the control volume. And there's this term control surface. Basically, this box that we define has 1, 2, 3, 4 surfaces, and we try to analyze what's going on each surface. So let's go through it really quickly. I'm going to number the surfaces. Simple, but make sure we got it. Surface 1, flow in, out, or nothing at all. Same thing for 2, 3, and 4. Well, surface 1, there's flow in. Surface 2, there's no flow in or out at that point. That is essentially parallel to the flow. Surface 3, there's flow out. And surface 4, there's flow neither in nor out. Sometimes there can be interesting devices where there's several of these flows. I just want you to be aware of that. Let's do an example to finish off class. Okay. Hey, just a quick note, more comment on organization on the course again. I'm trying to catch up myself and helping you guys, all of you catch up. I'll send out an email later on today. Tomorrow, I believe, my brother is going to be helping out with my dad. So for Thursday's lecture, I am going to record, but I hope that from 8 to 10:20, our official time, that I'll just be available via Zoom. And I think you can talk to me about concepts, you can talk to me about course. I'd like to talk to you really briefly about quiz 1. I'm not quite done with yet, I'm sorry about that, but there was some real good stuff. I know that many of you maybe felt time as a constraint, and there may be something to talk about there, but for sure there's something I want to talk with you about is, look, I know when you work a problem, it's very comfortable to copy down the problem and copy down the picture in detail. I believe for many of you it would help if you just skipped all that copying. Try to take the information given and write it symbolically. And if you need to do a diagram, make it really, really simple. And let's try to do that on this problem in practice for test 2. So the write-up would be a little bit more detailed than that, but I'll give you a second to look at it, and then I'll talk about it briefly. Okay, so let's say we got some hair dryer and it's operating at steady state, and the inlet diameter and the outlet diameter are the same. Kind of weird that it's given in inches. But anyway, the air actually goes in at 5 meters per second. What speed is it coming out at? So you could write all this stuff down on your paper, write it out. One thing I encourage you to do is write things symbolically. So I'll get this information up symbolically, which I don't think you even need to do in this case, but I'm going to try to write it symbolically and look for an equation. Okay, I tried to be efficient and get some basic information up there. The book is oftentimes in their solutions going to draw a control volume. So there is this volume through which the fluid is flowing over here like that green dashed line. And I labeled this point as 1, and I labeled the outlet as 2. Okay, and on my picture, I just, without writing it down, I didn't say temperature is equal to 27 degrees. I just wrote T1. Same thing, V1, T2, V2. Hey, the second part of if you try to think like of an overall problem-solving approach that we want you guys to have, and that is to read the problem, try to visualize what's going down, write down your given symbolically, and then after that, identify what you're looking for and try to find an equation that has that in it. You know, getting an engineering degree is not necessarily easily, but on the other hand, that general approach, that's why we're having you guys take Physics 11A first, is you should come out of Physics 11A being confident that that approach often works. Largely, that's what I'm looking for here from you guys here in Fluid. So I've written down some, not every bit of the information. I know what I'm looking for. Do I have an equation that has a V in it? Well, we have a ton of equations in it, so we could spend all sorts of time looking at it. What makes this a little easier is that we know that it's flow at steady state. It has the control volume. So I just went over the m.1 equals m.2 idea. Okay, we could use that. That doesn't have a V in it, but there's a version that does. And so that would be that rho 1, V1, A1 is equal to rho 2, V2, A2. And that has V in it, and that might be a good approach to do it. So I'd like you to think your way through it and see, hey, is there a way we could actually solve that? It may look a little bit tough, but we can. Well, first of all, the area, A stands for the cross-sectional area, and the area at the inlet and the area outlet are the same, so we can cross that out. So I'm just going to rewrite it without those two terms. Rewritten, I switched the order because I know I'm trying to solve for V2. All right. Hey, how are we going to actually get these densities? Well, we might think we could go to the tables. might say, hey, there's air here and there's air here, then we can go to the tables. But those tables, the tables for air are not at that temperature. And we know that air's density varies with temperature, so we can't just use one. How could we work it out? Well, we could use the ideal gas law. And of course, that's one skill that we want you to have when you work section 5.1. So a quick reminder that you look down at your, through your equation list, and I encourage you to do that with homework. We can get the density, okay, by doing P over RT for any gas. And if you think about this gas over here like this, we know its temperature. R we can look up, and we do know its pressure actually, because this is free right here like that. Remember, the pressure of a free fluid out in the atmosphere is basically going to be atmospheric pressure. That is either exactly right or a pretty good assumption. Okay, so we could get to work and work out the density of the gas here and the density of the gas there, and that might be a helpful thing to do. But let's see if we can be a little bit slick about it and do all the algebra first. So we're going to take this equation and solve it for V2 and see what it looks like. Okay, I had a mistake up here earlier. This should be V1. So V2 is going to be equal to rho 1 V1 over rho 2. That's what the equation is saying. And density, according to the ideal gas law, is P over RT. So it's going to get a little bit tight, but I'm going to try to get that up there. Okay, there is what we need to do. I've got 1, 2, 3, 4, 5, 6, 7 letters to fill in, 7 numbers to come up with. But hopefully you can look at this and say, hey, we can be a little bit slicker than that. So let's take a look at the R's. The R is what? It's the gas constant. It is universal. It holds any temperature. So this is air and this is air. So those two R's should be the same. Let's get rid of them. Hey, test yourself. Is there any other thing that we could get rid of or fill in easily? Okay. So P1, we could fill in 101.3 kPa. P2, we could fill in 101.3 kPa. Why? Those are free fluids, so they're exposed in the atmosphere. They're the same, so we could just cancel them out. So now we've gone from 7 terms to 3 terms, and that's not so bad. Writing the next line, I'm going to say it's equal to V1 times, I've got T1 down here and T2 here. This is in the denominator of the denominator. And so that's T2 over T1. Okay. And let's see how the numbers work out and see if we can understand what that's actually saying. So V1 was 5 meters per second. Remember, if you're using the ideal gas law, the temperatures need to be absolute. T1 was 27 at 273. So T1 is 300 Kelvin. T2 is 327, an unrealistic number for a hairdryer, but just trying to make the math easy. That's 600 Kelvin. Okay, and we get that it comes out at 10 meters per second. And there's our answer. There's our answer. So in this case, even though m dot in is equal to m dot out, v in is equal to v out, is not equal to v out. And the reasoning behind that is that as this air goes through there and warms up, it spreads out. It actually ends up spreading out. And so to get the same mass flow out as in, the air actually ends up speeding up. Okay. Well, that does it for the first part of what should have been Tuesday's lecture. I will be working on the second part of Tuesday's lecture, and then we should be getting closer to being caught up. Hopefully, I will get a chance to correspond with some of you either by email or Thursday morning from 8 to 10:20. I'll try to keep you posted on what's going on.